My name is Tan, and today I'll be discussing the basic principles of the fundamental theorem of algebra. It's fairly simple, so without further ado, let's get started. The fundamental theorem of algebra states that the degree of a polynomial determines the number of solutions that function has. Basically, this means that an nth degree polynomial has n number of roots. A root is an x value that, when plugged into the polynomial ax to the power of n plus bx to the power of n minus 1 plus etc., will give the function a value of 0. The fundamental theorem of algebra has three basic principles and parts to it. The first is the difference between even and odd degree polynomials. Second is the idea of complex roots and the fact that they come in pairs and conjugates. This is because the fundamental theorem of algebra has an extension in its number system that stretches from real roots to complex roots. And lastly, there's n behaviors, which is there to help us understand the idea of complex solutions more and to help verify between the number of real roots versus the number of complex roots. So first, let's start off with even degree polynomials. An example of an even degree polynomial graph could look something like this. So then this is a fourth degree function, and the fundamental theorem of algebra states that a fourth degree polynomial should have 4 roots. And if you look at this graph, we can find the 4 roots on the x-axis where the roots are found, because that's where, when this x value is plugged in, the function becomes 0, because y is at 0. So then this is a fourth degree polynomial with 4 roots, which satisfies the fundamental theorem of algebra. And if we try one for an odd degree polynomial, a graph could look like this. And this is a third degree polynomial, meaning it should have 3 roots. And the roots, again, should be on the x-axis, because the x-axis is where we find the roots. It's kind of like the roots line, because that's where there are zeros. So this third degree polynomial has, as we expected, 3 roots, which satisfies, again, the fundamental theorem of algebra. So let's move on to complex roots. So in reality, real roots is a subset of complex roots, and that's because real numbers is a subset and a branch of complex numbers. An example of a graph that has complex roots could look something like this. And this looks very much similar to the graph from before, but the one from before lied directly on the x-axis, with the 4 real roots being on the x-axis. This graph up here is a fourth degree polynomial, meaning it should have and will have and does have 4 roots. However, the roots aren't real because they're not on the x-axis. They're what we call complex roots, because even if it doesn't have a real root, because of the fundamental theorem of algebra, it has to have 4 roots. Now, to look at an odd degree polynomial with complex roots, we can consider this graph. So then if we look at this graph, there's only one real root, meaning that the other two roots that this third degree polynomial has to be complex, like the complex roots over here. However, the only difference is that the even graph has no real roots and only complex roots, while this graph has one real root still, while the other two is complex. That's because complex roots come in pairs. Over here, there are 4 complex roots, which pairs up perfectly. But over here, there's an odd number of roots, meaning that out of the 3, even if 2 of them are complex, one root has to be real. Complex roots come in pairs because complex numbers are conjugates of each other. So then, in order to understand this a little bit better, we can use the idea of n behaviors. So, if we were to look at the n behaviors of an even degree polynomial versus an odd degree polynomial, that can help us understand why an even degree polynomial can have no real roots, while an odd degree polynomial has to have a real root. So another even degree polynomial could look something like this. A second degree polynomial. It could either face up or down. The end behavior of an even degree polynomial is always going to be the same. Going from the origin to the left, if the graph goes up, the graph will also go up if you go from the origin and move to the right. Same for this negative even degree polynomial. Both sides will face down. One will not face down where the other face up. That sort of n behavior is for odd degree polynomials. Odd degree polynomials will always have opposite n behaviors, whether it's heading towards the positive on one side and towards the negative on the other side, or if it's heading negative towards one side and positive towards the other. It doesn't matter which way it starts with or which n behavior is on which side, whether the right side is positive or the right side is negative. It's the simple fact that an odd degree polynomial, an odd degree function, will always have opposite n behaviors, while an even degree polynomial will always have the same n behaviors. So, how does this help us understand complex numbers better? Well, as I said before, this x-axis acts as the root axis. It's where the roots lies, and now that we talked about complex roots, this is where specifically real roots lies. So this is what we can call the sort of real root axis. And so if you look at even degree polynomials, it can either, the function, the graph, can either exist above the x-axis or below the x-axis. It doesn't necessarily need to cross through the x-axis. And that's because the n behaviors are the same. Versus for odd functions, the n behaviors are in opposite directions, meaning that the graph, will inevitably have to cross the x-axis, as it does in this graph and as it does in this graph. So because of that, no matter how many complex roots the function has, it will always need to have at least one, because the graph has to cross the x-axis, so there will always at least be one. This sort of helps us understand the fact that complex roots have to come in pairs, because we can understand that there will always be one real root if the number of roots is odd, meaning there will never be an odd number of complex roots, but there will always be an even number of complex roots. And the fact that an even polynomial can have no real roots, but an odd polynomial must at least have one. So let's test this knowledge in an example. So say, for example, we are given this graph, and we are asked to find 1, the degree of the polynomial, 2nd, the number of real roots it has, and 3rd, the number of complex roots it has, or the pairs of complex roots it has. So if we were to look at this polynomial, we can first identify that it is automatically an odd degree polynomial because of the fact that the end behaviors are in opposite directions. This isolates us with the options of a 3rd degree polynomial, 5th degree, and etc. So we can tell that this is not a 3rd degree polynomial based on the amount of curves it has. We can count 1, 2, 3, 4, 5 curves at least, meaning this is at minimum, a 5th degree polynomial. Now, second is we have to find the number of real roots it has. As I said before, this is the line where real roots lies. So all we have to do is go across and see where the graph intersects this line. And it only intersects at one spot, here. So there is one real root. Now all that's left is the number of complex roots this function has. Seeing how the graph doesn't cross the x-axis more than once, the rest of the roots will be complex, not real. And since it is a 5th degree polynomial, the fundamental theorem of algebra says that there will be 5 roots, for sure. No more, no less. So that one of them is real, 4 of them must be complex. And since complex roots come in pairs, there will be 2 pairs of complex roots. Adding up to 5 total roots for this 5th degree polynomial, which satisfies and fits the fundamental theorem of algebra. Basically, in this lesson, we can take a graph and determine whether it's an odd or even function, its degree, how many roots it has, and from those numbers of roots which are real and which are complex, based on which ones cross and fall upon the x-axis. Thank you.